In this video we are going to understand that what is meant by the limit of a function, and we will also understand the important definition called the Epsilon-Delta definition of the limit of a function. We will first understand that what is meant by the limit of a function at a point. Let me start from an arbitrary function. Let it be f of x is equal to x square. You can easily draw the graph of this function, and it looks like to be this one in the first quadrant, and in the second quadrant it would be like this, which means that the graph of this function is a parabola. To keep the things very simple, I will just draw the first quadrant graph of this function. Note that at x is equal to 2, the value of the function is 4. So at x is equal to 2, is, for example, this point. Let's call it x is equal to 2, and we have seen that at x is equal to 2, the value of the function is 4. So at x is equal to 2, f of 2 is equal to 4, or it means that the value of this function is 4. Therefore we will write a 4 here. By the limit as x approaches to 2, limit as x approaches to 2 of this function f of x, we mean that we will have to check the behavior of the function as the value of x comes close to x is equal to 2. Note that we will have to check the behavior of the function as long as we come close to x is equal to 2, but we will have to come not at x is equal to 2. We will not come exactly at x is equal to 2, but we will have to stay much close to it. Let we come close to x is equal to 2 from right hand side. Let we come at this point. Instead, let we come at this point. At this point, let this is 2.1. At this point, the value of the function is about 4.41. or 4.4. Similarly, when we come more close to this point, the value becomes more close to 4, and if we come further close to x is equal to 2, then we will see from the graph that the value of f of x gets more sharpened and it becomes more close to 4. Therefore we are watching that as long as we come very close to x is equal to 2, then how the function behaves. Then the function also becomes very close to 4. Again, as long as we come close to x is equal to 2, the value of the function comes close to 4. Now we will check the behavior of this function at x is equal to 2 when we come to close to x is equal to 2 from the left hand side, from this side. Let we come at this point and let that this point is x is equal to 1.9, and at this point the value of the function is, you can check the value of the function at 1.9 and it comes to be 3.61, and I will write it 3.6. It is close to 4, but if I come more close to x from the left hand side, then I will see that the value of the function gets more sharpened and it comes very close to, more close to 4. Therefore, as long as you will come close to x is equal to 2 from the left hand side, you will see that the value of the function comes close to 4. We have seen that as long as we come close to x is equal to 2 from both left hand side and from right hand side, we see that the function is approaching to the value 4. Therefore, we will write that the limit of the function as x approaches to 2, this one, is equal to 4. Let we speak of the general definition of the limit of a function, and this definition is called the Epsilon-Delta definition of a function. The graph that we are using is still the graph of the function f of x is equal to x square. However, because we are speaking generally, therefore we have replaced this function by the general function y is equal to f of x. We noticed previously that how this function behaves as x approaches to 2. We saw that when x approaches to 2 from both of the sides, from the left side and from the right hand side, we saw that the function attains a value closer to 4. In other words, we will say that as x approaches to 2, then the function f of x, that is equal to x square, it approaches to 4. Therefore, the number 4 is called the limiting value of the function as x approaches to 2, or it is simply called the limit of the function as x approaches to 2. Now, because we are speaking generally, therefore we will not speak of the words 2 and 4. We will take some other general points. Let we say that instead of 2 we are writing a. Similarly, instead of writing the limit 4, we are using small l, lowercase l, instead of the limit 4, and this number l is the limit of this function as the function as x approaches to a, then this function f of x approaches to the limiting value l. We will now observe the behavior of this function as x approaches to a from right hand side, and then x approaches to a from left hand side. We had to do this because according to the criteria of the limit of a function, both the left hand limit and right hand limits must be observed and they must have the same answers. However, we have to observe this function from both of the sides of the point a. Let me mark 2 points, this point and this point, on the left hand side of point A and on the right hand side of this point A. This point is at the right hand side of this point A, and this one is at the left hand side. However, these are equidistant from this point A. It means that they have equal distance from point A. Therefore, if it is any number, for example it is 2.1 and A is 2, then this point is, as it is equidistant from this point A as this 2.1, so this point would be 1.1. This is x is equal to 1.1, and this 2.1 is also x, and this x is 2.1. This x is 1.9 and this is 2.1. Let we take the difference x minus A. It means that what is the difference between this limit, this point A at which the limit is to be tested, and this point 2.1. The difference is 2 minus 2.1, and it is it is 2.1 minus 2, 2.1 minus 2, and 2.1 minus 2 is equal to 0.1. Similarly, the difference between this point 1.9 and A, that is 2, is minus 0.1. Now, because we are speaking generally, therefore we will not make use of words like 2.1 and 1.9 etc. Instead of writing 2.1 0.1, I will say that I will assume that difference between point x, which is right here at this point, and the point A, the difference between these 2 points is, let we say that it is delta, when you are going from the right hand side to point A, from right hand side, RHS. Similarly, when you will approach to point A from the left hand side, then at this point that is highlighted here, the difference is negative delta. Obviously, in the previous case I told that this difference was when you are moving from right hand side to point A, the difference was 2.1, and when you moved from left hand side of point A and you reached that point, then the difference was minus 0.1, and instead of writing 0.1 and minus 0.1, I have written delta and negative delta. So this difference, as you reach from left hand side, then the difference between this point A and this point, which is x, is delta. Similarly, when you approach to this point A from the left hand side, then this difference is negative delta, as I have shown in this figure. So how can you justify both of these equations? These both of equations can be justified by taking the absolute value. That is, you will say that the absolute value of the difference is plus delta, because when you will take the absolute value of negative delta, the result is delta. So when you will take absolute value right here from the left hand side equation, then the difference is absolute value of x minus A is equal to negative times of delta absolute value, and it is again delta. Similarly, when you will take the absolute value on the first equation, then the result is again delta. One more thing that needs to be kept in the mind is that when you are dealing with the function as its limit x approaches to A, it obviously means that you are not exactly at the point x is equal to A. Therefore, the difference between these 2 points x and A, it cannot be equal to 0, since we have taken the absolute value of this difference x minus a, therefore it cannot be negative. It means that it must be positive, and therefore x minus a absolute value is always a positive number. It is greater than 0. Therefore this delta is also greater than 0 because absolute value of x minus a is greater than 0. Next, at the point x, we are still at this point x, and at this point x the value of function is f of x. The value of the function corresponding to this point x is f of x, and the limiting value is L. Since there is difference between this point x and a, therefore there is also the difference between the value f of x and the limiting value L. So I will say that if there is difference between x and a and it was equal to delta, it is equal to delta, I am saying that the value of the function corresponding to the point x is f of x, and the value of the function corresponding to the point a, it is the limiting value of the function, and it is supposed to be L. And there is the difference between these 2 points, therefore there is also the difference between these function points, as it can be seen in the diagram. The limiting point is down here, and the value of the function at point x is this f of x, and we can clearly see that there is the difference between f of x and L, and we say that let this difference is epsilon. It means that this difference is, I am saying that let it is epsilon. So I will write that at this moment the difference between f of x and L is equal to epsilon, and from the left hand side this would be minus epsilon, therefore we will take the absolute value to justify this. Now because we are still at this point x, we are at this point x, and we further need to move more close to this point a, therefore we will take this point more close to this point a at which the limit has to be evaluated, therefore we will move more close to this point a. When you were at this point x, then the difference between x and a was delta, and when you will move more close to this point, for example you are at this point here, then this difference, now the difference between this point x and this point a becomes more smaller. Previously this difference at this point, the difference was delta. When you will move more close to point a, this difference would be smaller than delta, obviously. So we will write down here that this difference x minus a is equal to delta. When you are moving more close to point a, this difference x minus a becomes more smaller, and it becomes smaller than delta. Similarly, when this difference becomes more smaller, the function value also becomes closer to this value L, and therefore this value f of x minus L absolute value, it also becomes smaller than this value epsilon. So we will write that f of x minus L is less than epsilon. It can again be justified by the use of the figure. Note that previously the difference between f of x and L was epsilon. As you moved more close to point A, now this is you are at this point. When you will come at this point, then the value of the function will become more close to this point L, and this point is f of x. Now the difference between f of x and L is this one, which is more smaller than epsilon. Therefore I wrote that the difference f of x minus epsilon is less than f of x minus L is less than epsilon. This statement now completes the definition of the limit of a function. I will again just state this definition. Note that this epsilon is also positive because you are taking the absolute value. It cannot be equal, it cannot be less than 0. That means it cannot be negative, and it can also it cannot be equal to f of x cannot be equal to L, because you are approaching very close to L, not equal to L. Therefore this difference cannot be equal to 0. Therefore this epsilon is always greater than 0. However small it may be, it must be greater than 0. Now I will speak the definition in the general language. I will say that let A is a real number. Let we speak that A is a real number. Then if limit of the function f of x as x approaches to A, if this limit is L, if the limit x approaches to A of the function f of x is equal to L, then it means that for every epsilon greater than 0 there is delta greater than 0, that is mentioned by me. There exists delta greater than 0 such that this inequality holds. This is inequality number 1. This inequality holds whenever this inequality, absolute value of x minus A less than delta, this holds. So I will say that this limit of the function f of x as x approaches to A is L if for every epsilon greater than 0 there exists delta greater than 0, if absolute value of f of x minus L is less than epsilon, whenever absolute value of x minus A is less than delta, as already mentioned. And I have already mentioned that x minus A absolute value is always positive, it is greater than 0. Therefore I will write it here that absolute value of x minus A is greater than 0, or 0 is less than x minus A. So this is first inequality and this is second inequality. This completes the definition of the function, limit of the function in the sense of epsilon and delta. I think that it was quite clear to you. In the next lecture I will give you some examples and we will use this definition in proving the limits of the function. Thanks for watching.